this is Junichi Horikawa, and from today I'd like to start a series called VEX for algorithmic design. And in this specific series, I'm going to show you how to learn a basic of VEX in order to use it for algorithmic design and procedural modeling. And today I'm going to teach you the very basics of attributes, which is pretty essential in order to use VEX. First off, we're going to start by knowing the types of attributes. There are mainly 4 types of attributes. One is point, one is primitive, one is vertex, and one is called detail. And let me draw a sketch of a polygon to explain what these attributes are for. So the first one, the point. The point is the point which construct this polygon. So currently you have 4 points, and each point can contain an attribute, different attribute. So that's point. And if it's polygon that you're working at right now, then these faces will be called primitive. So each face, in this case 2 faces, can have different attributes. Just this one. This primitive attribute can be also stored other than faces. In some cases, you can treat those edges, each edges, as a primitive, or at some cases you can call the whole geometry, like a mesh, as a primitive, as a single primitive. So this primitive attribute can be very versatile, so remember that one. And the vertex, the third one, vertex, is pretty similar to point, but the difference is that the vertex is stored for each primitive. So for, say you are looking at this primitive, this triangle face, and each triangle face has its own unique vertices. So for this one, you have 1, 2, and 3 vertex. For this one as well, you have another 1, 2, and 3 vertex. So that's a bit different compared to the point. For the point, you only have 4 points in this case, but for vertices, you have 3 points, 3 vertices for each primitive. So that's the difference. And it is often used for UVs in order to map the textures. So most of the time, what you're going to work with is this point and primitive, and sometimes if you want to deal with the UV as well, you use vertex as well. And finally, you have an attribute type called detail. So the detail is a bit special. It is an attribute which can be attached to a whole object. So, which means is the object that's can be outputted from one of the node that you're using right now. So one object can have only one detail attribute, so that's what you have to remember. And this detail attribute is useful when you want to store some information which it can be applied for a whole object, not for each point, not for each primitive, but if you just want to have the attribute which shares all over the geometry. So that's the 4 different attribute types. So let's check that 4 attributes in Houdini UI, what it looks like. Okay, so first of all, I'm going to create a geometry node inside the object network. go into it by double clicking it. And let's try to create some simple geometry like sphere. And let's make it as polygon. Alright, so currently you have a spherical object like this, and in order to check what kind of attribute this sphere has, first thing you want to do is to show the geometry spreadsheet window. The place where you can show the spreadsheet is right here. When you go to the right top corner, you see this plus sign icon. Click this, and from there you should see a geometry spreadsheet under inspectors menu. Click that, and this window will show you all the attributes which this sphere has. And on the top part of the spreadsheet, you see 4 types of icons, and each represents the attribute types. The first one is points, second one is vertices, third one is primitive, and the last one is detail. So if you click to each of the icon, you see the attributes stored in each attribute type or geometrical type. So in the points, currently we have 3 attributes called px, py, pz, which corresponds to the point position of each point shown in this display, which corresponds to this sphere geometry. And if you look at the left side, you see this number starting from 0 to all up to 41, and that is corresponding to an index number of each point. And currently you don't see any numbers here, but when you click this button on the middle with the point with the numbers, and let's also set the size of the text a bit bigger. So these numbers that's shown in the display corresponds to the index number right here on the left side on the geometry spreadsheet window. So if you look at the point 1 or number 0 point, which is this one, it corresponds to the first point on the geometry spreadsheet, and the position says the x value is 0, y is 0, and z is -1. And if you look at carefully at the grid, you can see that this represents the position of this point. When you go to the Vertex tab, what you see is a bit different index format compared to the points. And here you see 0, 0, 0, 1, 0, 2, and so on. The first 0 or 1 or 2 indicates the number of primitive which you can check it from by toggling this icon on. So by toggling this, you see a number on top of each primitive, and that is the number of primitive. So this is the primitive 0. So this 0, 0, 0, 1, and 0, 2 are all indicating the vertex index for this specific primitive. And if you look at the attributes, there are one attribute called point num. So and this corresponds to the actual point number, which can be shown by clicking this one. So as you can see, you have for primitive 0, you have point number 0, 1, 2. And if you look at the index, if you look at the attributes, you also see 2, 1, 0 right here. So when the point number is equal to 2 for primitive 0, which is this one, then the index of vertex is 0, 0 right here. If it's 1, it's 0, column 1 right here. If it's 0, column 2, and if the point number is 0, then it's 0, column 2, and so on. So that's how you check which vertex corresponds to which point and which primitive. And you're going to use this when you want to use like a UV and so on. So next thing is a primitive attribute. And currently you don't have any primitive attributes stored in each faces. You just have this index number, which corresponds to the red label shown in the display right now, which is displayed on top of each triangles. But currently we don't have any information here. When you go to the fourth tab, which is called Detail, currently you don't see any attributes assigned to this sphere, but this is the actual attribute place where you can store the attributes for whole object that you have selected. Not for each point, not for each primitive, but for whole object. So that's the differences between each attribute type. And let's try to use all of them by writing a really simple VEX script. In order to write a VEX code, in order to work with a attribute for each point, primitive, or VEX, or vertices, or detail, what you often use is a attribute wrangle node. By right-clicking the canvas, you can search for a wrangle, and you see some different types of wrangle node, and what you often use is this point wrangle, primitive wrangle, vertex wrangle, or attribute wrangle. Other ones like deformation wrangle, height field wrangle, and volume wrangle is a bit special. I'm gonna explain in other videos, but for today I'm going to use point, primitive, vertex, or attributes. So first I'm going to place this point wrangle under the sphere, and let's connect the sphere with the first input of point wrangle right here. The point wrangle node is a specific node to write a VEX code in order to access or modify or do the vector operations for each point which comes from the input geometry, in this case a sphere. So let's try to set some custom attributes to each point of the sphere right here by writing a simple code inside this text editor. In order to set or get or modify the attributes stored in each point, the primitives, and so on, you first need to know the types of data that you can store in an attribute. So let's check that out by going into a document for the VEX inside a SideFX document page. And when you go to the VEX page, you see several pages. Go to the using VEX expressions, and under at some pages in the middle, you see a list of types that you can store as an attribute. And there are mainly 9 data types that you can store as an attribute. But mainly what you need to know is this float value, which is a floating number value, and vector, which is the vector 3 value, which indicates the value x, y, and z, often used for positions or directions and so on. An integer, which is an integer value like 1, 2, 3, 4, 5, and so on. And sometimes matrix used for transformation, rotation, scaling, and so on. And last of all, string, which is used to store the text data like ABC and so on. So these are the important data types that you have to remember. So let's try to store some of the data type as an attribute to each point. And in order to access to each data type using the VEX, there are some syntax that you can access to each attribute easily by writing like these. So if you want to access a float data type attribute in point attribute or primitive attribute or anything, you write like f at attribute name. If you want to access to the or modify the vector 2 attribute, then you write like u at attribute name. So let me show you in the Houdini window. So say you want to set a float attribute for this point, for each point, and to do that you first write f at, then you specify the name of the attribute. In this case I'm just going to name this f val, then write a code equal, then just put any value that you want to set as an attribute to each point. Okay, so that's it, and when you finish writing it, click some empty place in the canvas, and in order to see the difference, in order to see if the value has really been stored as an attribute to each point, you go back to the geometry spreadsheet and go into the point tab, and there you should see a newly created attribute called fval, and at each point you see these numbers applied at each, stored at each point. And just by writing, you can see that just by writing one line, the value has been applied to every point exist in this sphere geometry. So that's how point wrangle works. This is more like a multi-threading operation. By writing a code in a point wrangle, this operation will be applied to each point in the same manner. And this makes the VEX code operation be really fast compared to a Python code. Because for the Python, you cannot do a multi-threading operations for all the points. You have to process the code one by one for each point. But for VEX, you can apply the code to each point at once. So that makes the process really fast. And so most of the time, if you do the geometry operations, if you want to do the geometry operations, you want to use VEX instead of Python. Let's try another types of data. Let's say you want to apply an attribute for the integer. Then in that case, you write I at, then set the name for the integer value, then create a integer value and store it using a equal character. Let's check this again. There you see a value 100 being stored at each point. Try this with the string s at sval. This is a character. When you want to use a string, you want to use this double colon in order to determine that the character which has been written inside this double colon is the string. So when you go back to the geometry spreadsheet, you see this string being applied as an attribute. Okay, let's also try to store a vector attribute. I'm gonna call this vval, and in order to create a new vector value, there is a specific function called set. Write a set together with a bracket like this. Then inside you have to set 3 types of values, which is corresponding to x, y, and z. So for the x, let's say 3.0, and divide the value, or split the value, separate the value by comma right here. And for the y, let's say 6.3, and for the z value, let's say 1.4. So you have x, y, and z separated by this comma and set as a function inside this column. Right. So by writing like this, go back to the geometry spreadsheet and you should see 3 values applied into a point attribute, and each of them has a value number index together next to this name of the attribute. So the first one is called vval0, the second one is vval1, and the last one is vval2. This 0, 1, 2 corresponds to the x, y, and z. And if you go back to the left side, you see something similar, which is p. Basically, the meaning of these 3 values and these 3 values that I've just created is much the same. So p, capital P attribute is also a vector attribute, which corresponds to the position of the point, actual point. And these one are the custom vector attributes that I have just created. And other than these different types of data, you can also store one called array of datas. Array means a list, and at each attributes you can also set a list of specific data type. Something like a list of float, a list of integers, a list of strings, and so on. In order to do that, if you want to store a list of float value, then first you type F and then write a character square bracket, then type at, then after that you specify the name of this attribute, let's say eval. And in order to create an array, you type array and then create a bracket, and inside you type a list of float value that you want to store as a list. So say you want to store 4 types of numbers, 4 different numbers like this. By doing it, and if you go back to the geometry spreadsheet, you should see a newly created attribute called eval, and at each point you see that the float array or float list has been stored as an attribute, which is enclosed by a square bracket, and you see 4 different values stored in for each point. So that was how you can store a attribute at each point with different data types. Basically, you can do the same for primitive, vertex, or detail. There are different ways to change the attribute type that you're going to store to. One way is to change this runover parameter. Currently this is set as point, so meaning that this wrangle works on each point. But by changing this to primitive, this whole code will be changed to modify or set the attribute for primitive. So if you go back to the geometry spreadsheet, there are no more attributes on point, but when you go to the third tab, those new attributes that you have just created have been stored in each primitive. Same for vertex and detail. If you go to a vertex, go back to the geometry spreadsheet, go to the vertex tab, you see this attributes being created for a vertex attribute. Same for detail. If you set it to detail and go back to the geometry spreadsheet, check this detail icon, you see all the attributes has been stored as a detail attribute, and it looks a bit different compared to a point, vertex, or primitive, because detail attribute is stored as one object. So for one object you only have one attribute, so that the layout is a bit different compared to other points, vertex, or primitive. Another way to access to different types of attribute is by using a different node. Like if you want to access to the primitive attribute, then you use primitive wrangle, and it is basically the same with this point wrangle, only the difference is that the runover parameter is different. It is set as primitive as initial value, and that's the only difference between this point wrangle and primitive wrangle. You also have vertex wrangle, which is the runover is set as vertex as initial value. Unfortunately, there are no detail wrangle, so if you want to use a detail runover, then you have to place one of the wrangle right here: point wrangle, primitive wrangle, vertex wrangle, or maybe attribute wrangle, which is same as point wrangle. I don't know why they made 2 different wrangle with different names, but this is essentially the same. This is essentially the same with the point wrangle, but by if you want to use a detail, just change the runover to detail, and there you can use this as a detail wrangle. Okay, so that was for setting an attribute to each attribute type. In order to retrieve the attribute that you have just been set for a point, let's try this out by creating another wrangle, point wrangle. Then connect this to the first input of this point wrangle. And let's check the geometry spreadsheet first and go to the point parameter. And you can see that all the parameters, all the attributes that has been stored right here has been transferred to the new node as well. So from there, what you want to do is to access one of the attributes which is stored in each point and use that information for some purpose. So let's try to do that. In this case, I'm going to access to a float attribute value and use that to move each point to X direction with that value. So let's try that out. In order to access the float value or any attribute values which is stored in each point, what you just need to do is to say if you want access to the float type attribute which is named as fval, you just write like this. So same as accessing to a float value like this. Same as storing a float value, you just type f at fval in order to access to its value and use this value to, let's try to use this value to move the point to X direction. So you also need to access the point position attribute, which is equal to, back to here, capital P. So, and that's the vector type. So in order to access the vector type capital P attribute, you type like v at p. And in order to access the x value, specific x value of this p, you type like dot x. And try to modify this x coordinate of the point position using this f at fval. And when you finish writing the code, you also need to write this semicolon at the end all the time. So I forgot to explain it, but for every code you have to type semicolon on the last. Okay, so by typing like this, by setting an x coordinate with this f value, you see that whole point x direction or x coordinate has been changed to something 1.5 or so, which corresponds to this one. So by changing this f value on the first point wrangle maybe to the negative 1.5, then the whole point has been moved to that specific coordinate by accessing to a point attribute called fval, which is this one. So that's how you can access to a attribute at each data type. Now you have just set your custom attributes to each point or each primitive, but there are actually some special attributes which the name is preserved by Houdini and used for special cases. And you already have used one of the attribute, which is this at p, which is the point position value. Now there are a lot of other special attributes for each point or vertex or primitive or detail, and all of these shown in right here is mostly used for a point. Like axle is used for acceleration value, which is often used together with the dot network for the dynamics. CD is a color node, a color attributes which can be used for a point, and primitive normal is the normal directional value, which is the vector type, can be used for point and primitive as well. Scale is a scale value which can be used together with the copy sub node for a point mostly. Force is also a DOP related attribute, can be used to determine the force with the directional, how much the point should move to which direction, and so on. So you have a bunch of specialized attributes which can be used for many purposes or special purposes. And there are some special attributes which you use a lot when you do this algorithmic design using VEX. So let me just show you some of the frequently used attributes. Okay, I'm going to create another point wrangle, then connect with a sphere. Okay, first of all, I'm going to show you how you can access to a point position, which I have already done right here, but it was v at p. I have specifically determined as a vector data type, but actually if it's a specialized attribute like at p, which is shown in this document page, you don't necessarily have to determine the type of data. The Houdini will guess what this type is by writing this specialized attributes. So in this case, you don't need to type v if you don't want to. You can still use that, but it's not necessary. If you are using your custom attributes, then you have to define what the data type is. But if it's a specialized or preserved attributes, then you actually don't need to specify the data type that you're setting or retrieving. Now let's try to move this point position using some random value. So in order to change the point position, just like I did right here, point x at p dot x equals something. But in this case, I'm just going to update whole position vector. So in this case, before I was just setting the x coordinate, but for this one, I'm going to try to update the whole vector position. And in order to do that, I am going to use the random value. And in order to create a random value, you can use a function called rand. Use a bracket, a parenthesis to close the function, and inside this parenthesis you have to input some parameters, which will going to be the seed number for random value. And I'm just going to type the same position value inside rand in order to create a random value. So by having a different value for the random, you always get different value. If you just use the same value inside the rand parameter, then you always get the same value. At p is always different for each point, so as a result, each point should get a different random values using this rand. And as a result, by changing this at p value, each point has been placed at really random position like this. And if you go back to the geometry spreadsheet at point, you see that each point has different value. But by changing the value inside the rand to the same value for each point, like say 1, then the whole point has come to this point right here. And if you go to the geometry spreadsheet again, you can see that the whole point position is exactly the same. So in order to create the really random value for each point to be different, you kind of have to use a different value for each random seed parameter here, right here. And it is often used, the at p value is often used together with the rand like this in order to change the point position different for each point. So that was how you can access to this one of the preserved or special attribute called at p. Let's also try another attribute, and in this case let's try to change the color for each point. And in order to access the color, you type at capital C lowercase d cd, and that's the vector type attribute for the color. And in order to change the color you have to create a vector value, so which is going to be x, y, and z. And 0, 0, 0 means RGB value is 0. All the RGB is 0, equal to 0, and that means it's black. So if it's 0, each point color become black like this. If it's 1, 1, 1, then that means the color is white like this. So if you want to set it as red, then you only set 1 for R value, which is equal to X value, and for G and B, which is equal to Y and Z, you set 0, and as a result you can set the color as red. You can also use random as well, and random can create random vectors or sometimes random float value or random integer value as well. In this case, I have used it for color, which is the vector type, so automatically this rand function will create a random value for the vector, which is in between 0 to 1 for each x, y, and z coordinate. So as a result, each point will have a different color value like this. So that's one of the special attributes you used in Houdini in order to change the color. And let me just show you one more special attributes you use often or frequently, which is a point number value for this point. The point number value is corresponding to this left hand side column, which goes from 0 to 41. So currently you have a total of 42 points, and this left hand side value is called point number, and you can access to that number inside the VEX code, so that in order to make the point modification based on those point numbers. So let's try to access it, and that specific attribute is called ptnum. If you go back to the document page, you see a name called ptnum at ptnum. So that's the actual attribute name for in order to retrieve the point number. Next to it, you have some similar name attributes like primnum, vtxnum, or numlength, or so on. As you might have imagined, at primnum is a primitive number value for each primitive. VTXnum is a vertex number value, and so on. But when you are working with point wrangle, when the runover is set as point, what you can get is only the point number. Even if you try to use the prim number, you cannot access to the primitive number because the runover is different. So when you are on the point runover, a point wrangle, only the number you can use is this ptnum, which is corresponding to the point number. So let's try to see if you have really get the value by creating a new integer attribute, say called n, then store that point number to a attribute called n right here. And let's go back to the geometry spreadsheet and see how it looks like. And as you can see, you have an attribute called n, which is equal to the point number on the left side. So as I told you, since we are inside the point wrangle runover set as point, the ptnum works, but if you change this to some of the different attribute like primnum or vertexnum, you kind of get some weird result. Let's say if you change this to primnum, go back to the geometry spreadsheet and look at the n, you still see some changes on the n, but it is not a point number right here, but it is actually the primitive, one of the primitive number which is attached to the point, which is using this specific point. So if you look at the point, say number 4 right here, you see that it is connected with 4 different, 1, 2, 3, maybe 5 different triangles right here. And if you go back to the geometry spreadsheet and look at the number 4 right here, you only see one n which is one of the primitive number right here, and which is currently set as 1. And if you check, there is one face attached to 4. The primitive number is equal to 1 right here, but actually there are other primitives attached to this number 0.4. But using at prim num cannot retrieve every point number, but just can get one of the primitive number attached to the point. So most of the time, if you cannot retrieve all the numbers possible, then it's not really useful. But there are other functions which you can retrieve all the primitive numbers attached to the points, and I'm going to explain in different videos about that. But just using a at primitive number inside a point wrangle doesn't really make sense, so try not to use that. But if you want to use the prim num, then try to change this to primitive, then use prim num, and as a result you should be able to get a primitive number which corresponds to the left hand side value like this. So the run over types and what attribute to use is pretty important when you try to think about what kind of data to use, right? So now I have just set the run over to primitive, and some of the outlook became different. Now the first line doesn't seem to work now, because at p is actually a point position value, but so the primitive attribute or the primitive attribute doesn't really have a specialized attribute called at p, which is only for the point. But if you go look at the color attribute, actually each faces has been changed to different colors. So that means primitive also has an attribute called at cd as a special attribute. So you can use at cd for primitive, but actually you cannot use at p for primitive. But there are you can actually use at p in primitive as well, but just to retrieve the center point of each primitive. So it's not actually a point position, but actually become the center point position of the primitive. But as you can see, you cannot really modify the center point position using something like this. What you can use for at p in primitive is just to retrieve the center point position. You cannot really actually change that value, right? So that's kind of a different between the attribute types, what kind of attribute you can use and what kind of attribute you can not use. And all of that information can be retrieved from this document. So if you want to look further, if you want to know more about this kind of special attributes, you can go look into this. But I am going to also show you a lot of other special attributes using some examples in different videos. So if you follow that video, I think you get familiar with all kinds of special attributes as well. And there are one more special attributes that I want to show you, which is called as global attributes, which can be accessed from any attribute types, from points, detail, primitive, vertex, or even numbers. Which is one of the example of the global attribute is called frame, at frame. So at frame indicates the frame value, the current frame value for Houdini, and that is equal to this value right here on the timeline, which currently is 1. If you set it to 81, then at frame will be the value 81. So let's check this out by creating another integer attribute called frame, I at frame, and store this at capital F frame. as an attribute, as a custom attribute frame. Maybe let's change this name to something different, FR, like this. And let's see if you have got this at frame attribute correctly. And if you go back, if you go to the geometry spreadsheet for currently, is it on primitive? Yeah. So I have just set the primitive attribute called FR. And if you go back to the primitive attribute in the geometry spreadsheet, you see a new attribute called FR and stored 81 right here. And let's try to change the frame and see that this FR value is changing corresponding to the frame position, like this. See here? And this kind of attribute is called as global attribute and can be accessed with any other attribute types. If you change this to point and go back to the geometry spreadsheet to the point, you still see an attribute called FR, and which can be changed by changing this frame as well. So these are more special. These attributes are more special. You can also check that in a document. And there are other global attributes like time. And for the time, you can access by writing at capital T time, like this. And time indicates the time that has been used from a frame 1 in seconds. So in frame 1, the value should be 0 second. So if you go back to the point geometry spreadsheet and look at the time attribute, you see 0, but by increasing the frame, the value increases, and this indicates the seconds which is on this specific frame. So in the end, the time becomes something close to 10 seconds. So that is a global attribute which you can access from any attribute type. Now let me just finish this first video in order to explain the basics of VEX by using a detail wrangle. So in order to use the detail wrangle, first you need to create one of the wrangle node, which in this case I'm going to use a node called attribute wrangle. Set it to right next to the point wrangle right here, and connect this to a first input, then set the run over to detail. So previously, when we were dealing with primitive points or vertices, the code written here was running on each point, each primitive or each vertex simultaneously, meaning something like multi-threaded. But when you use detail, the code only runs once. So you can only do one operation, which only works for a whole object, not for each point, not for each primitive, not for each vertex, but only for this specific geometry. Meaning it's not useful when you want to change the attribute for each point or primitive or vertex, but it is useful only when you want to store or modify the global attribute for this specific geometry. For example, like the value like time, we have set the time attribute to point for each point like this, but actually you don't really need to have this time attribute which is always the same to each point, which is not really necessary. For value like time, which is global, which doesn't change for each point, you can just store it as one value for this whole setup. So that's when you want to use detail wrangle or detail attribute. So say f at time equals at time this. In this case, the detail attribute only has one attribute for each object, so you only get one attribute attached to the detail. So you don't have an unnecessarily attribute for a point, vertex, or primitive, which will be stored at each point or each primitive. And we are going to use this detail attribute, detail wrangle, a lot as well in terms of algorithmic design later on, so please keep that in mind as well. So this was the first video for the VEX for algorithmic design, and I have focused on the attribute types and data types. And on next video, I would like to show you how to use some various functions in order to access and modify the attribute in more flexible way. And I would also like to focus on group, which is used to filter geometries. Okay, so this is it. And if you found this video interesting, please try to follow the video that I'm going to create for this series, VEX for algorithmic designs. And in the end, by going through all the videos that I have going to create, you should be able to use VEX for your own algorithmic design purpose or procedural modeling purposes. Okay, thank you very much, and see you next time. Please subscribe if you find it interesting.